Hi, everyone. Thank you for joining. Just gonna give it one more minute, have more people come into the meeting, and then we will get started. All right. Well, while everyone's still joining, I'll get started with some housekeeping. Hi, everyone. Thank you for joining the webinar today. This one will be recorded like usual and sent at the end of the week along with the presentation slides. If you have any questions, feel free to throw them in the chat or the Q&A, and we'll get to questions at the end. Also, feel free to raise your hand and we can take you off of mute so you can ask your question live. But other than that, I will hand it over to our presenter and get started. Thank you.
Thank you, Kate. Welcome, everybody. Good afternoon. I'll be your presenter today. I'm Chris Salerno with Linkus Incorporated. We support, as a subconsultant under ICF, we support the Gas Emerging Technology Program for various different projects, mainly the field studies. And so today I'll be presenting results from our smart pump multifamily pilot study, which examines and evaluates the performance of smart recirculation pumps in specifically multifamily and or apartment buildings under domestic hot water applications. So you can see here it says domestic hot water. That's another term used for these systems that produce potable hot water for tenants. So that's opposed to traditional space heating applications. So this specifically looks at multifamily domestic hot water applications. So before we dive into the details, I'd like to give you guys a little bit of a roadmap of where we're headed today. So at the start, we'll just start with the big picture and kind of summarize what we found and provide some of the key takeaways and findings. Then we'll walk through the different objectives that were outlined and how the technology works to meet these objectives. Then after that, we'll dive into the different site descriptions to give you an idea of the different sites that were used and selected for this, specifically selected for this study. And then we'll dive into the actual the energy savings results, which were measured, being gas and electricity savings. But it should be noted that this is a SoCal gas study, so the focus is on gas energy savings. Then following that, we will do a summary discussion on what we found and what worked at different sites and compare different savings under different smart control modes for these smart pumps. And then also additionally, we'll be covering presenting quickly some real world installation costs to be considered, specifically materials versus labor, and then finish with some recommendations for programs, manufacturers, and building owners for these smart pumps. So my goal is to keep this brief and practical, but feel free again to throw questions into the chat, and I'll try to leave at least 10 to 15 minutes at the end of the presentation. So if you have anything that comes up along the way or is off topic, just feel free to keep that to the end of the conversation, and we'll be glad to answer that as best we can. So to begin, let's jump into the executive summary. This kind of follows the general outline of the published report. So again, if you want more details on specific findings and numbers and methodologies, I'd refer to you to the actual report that's been published for this project. So I will definitely go along with the report findings, go through the executive summary to provide kind of a high level. But I also will try not to get too much into the details so I can provide just kind of a high level overview, and then so that we get a good picture of the outcome of the study. So for this smart pump study, we were able to evaluate two different smart pumps, mainly Grundfos smart pumps. So specifically at site number one, we did use a Magna 3 smart pump, and I'll go into detail or show you pictures of what this looks compared to the other Grundfos smart pump that we use, which is the Alpha HWR, used at sites 2 and 3. The reason for this is that at the time of the study, this initiated in 2023, the original Grundfos Alpha HWR, these being smart pumps in the series are a series of smart pumps that provide similar smart pump capabilities. Unfortunately, when we were starting the study, they discontinued the Alpha HWR, which is a smaller, more specialized pump for these applications. So with that in mind, we had to resort to using the Magna 3 pump, which is actually a larger Grundfos smart pump, which is more geared towards larger commercial applications. So we'll go into detail the impact that has on the energy savings and such. So it is to note that we use different pumps with the same capabilities throughout the site. So again, these are where we were conducted across three multifamily, what's the MFM means, at which were all in the California Climate Zone 3. So this is in the San Francisco Bay Area. Um, and specifically, all these sites had centralized gas domestic hot water systems. So that was key. So the objective, or what we did through the study, is that we monitored baseline data, that being gas temperatures and flows data, over at least 1 month on the baseline being the existing constant speed pump, and then moving on and installing the smart pump, and then monitoring 3+ months using different control modes. So 3 months under one control mode, and then 3 months under a different control mode to accurately quantify the savings under varying demand patterns. So obviously, the main objective of the study, as mentioned before, is to quantify gas energy savings. Electricity is kind of a secondary benefit. And then there was to compare the different smart modes used for these smart pumps, and then lastly, document the cost and identify the different barriers that were identified along the way to adopting the smart pump. So some of the key findings here, you can see that there's two different modes that are learned that were used in this study. One being adaptive learning, and the other being constant temperature mode. And we'll go in more detail of what these are. Um, but specifically, you could see here that the gas energy savings varied quite a bit for the adaptive learning, being 1% to about 20%. The reason for the 1% is that the oversizing of the pump at site number one did not allow for the larger pump to adapt at the lower flow limits, which were below the limits of the pump itself. So fortunately, it did not perform as expected. However, constant temperature mode provided about 8% to a 14% pretty consistent savings across each site, regardless of the sizing of the pump. Additionally, the electrical savings varied pretty consistently, except for site number one. Because of that much larger pump we had to use, it resulted from the baseline pump to that larger pump and about 200% increase in electricity. So this can be obviously what do you call it? This could be prevented if the proper size pump is not is used at the site. So this is something to note, but across all the other sites with the proper sizing pump and it operating in a correct mode, it showed about 65 to 94% electric savings. Overall, considering all control modes, we found about a 16.4 therms per year per dwelling unit. So this is per multifamily dwelling unit. It provided about 16 therms per unit per year. This compares to about 13.22, which is the deemed value taken from the SWWH015 demand controller response for some central multifamily systems. So we could see that overall, regardless of the variation in the savings and the variation in performance across sites, we did find overall that the smart pumps were able to provide at least about a 20% overall savings increase compared to the relevant measure package SWWH015. In terms of the adaptive learning, this was the default mode for these smart pumps, as these are thought to be more plug-and-play applications that you can replace the existing constant speed recirculation pump with the smart pump in adaptive learning mode, and that it's able to have the capabilities to be able to meet the needs of that system. However, the adaptive learning does require an initial learning period, in that it needs to adapt and learn the different draw pattern behaviors for each of these sites. So we did not see that initial behavior. We did not see tenant complaints during this initial behavior for all sites, but specifically sites 1 and 3. And based on what we found with the study, it was not conclusive on why that was. So there was really a consideration for the need to balance that low temperature for adaptive learning, but also to balance that with the tenant comfort so that there's no complaints during that. So with that in mind, we did find that a key barrier from the study was that there was kind of an inadequate manufacturer guidance on what and how to implement these different control modes, specifically on domestic hot water applications. More specifically, I'm referring to is the different temperature settings that are required, say for the adaptive learning during the initial learning period, so that you are preventing any tenant discomfort or complaints in that, so you're not disrupting the hot water service. So it would have been better if the manufacturers would have been more clear on the guidance through their mobile app used to be able to set these Grundfos smart pumps up. It would have been better to have more clear guidance on what those temperature limits should have been. And so at the end of the day, after what we've learned from optimizing the different settings, we found that using the constant temperature mode was the preferred mode, in that it was able to prevent any significant tenant complaints on hot water, and then that it provided consistent savings across each site at the same time, without um, without tenant complaints. So with that, we were able to consult with the manufacturer and come up to a optimized strategy for those temperature limits to be able to provide guidance for future studies and such. So we found that the optimal temperature range for this smart pump to be able to turn on and off is about 10 to 20 degrees below 10 to 20 degrees below the supply temperature. So, for example, if the supply temperature of the system is at 120, ideally you would want the pump to run until it reaches 110, and then turn off until the temperature reaches down to 100. So there's that 10-degree buffer. And really, this minimum temperature really has to do with the site-specific tenant preferences. You know, some sites, the tenants are used to having 130-degree water versus other sites where they're not used to having that level of degree of hot water. So it really comes down to the site-specific applications. What is the different set point, and what are those different what is the lowest range of temperatures you can put the pump at, so that it maintains that tenant comfort, but however it's reducing the return temperature, which is resulting in energy savings and the overall gas energy savings. So it was very important to find that that certain settings for each site, and we found this generally worked, given that the supply temperature changed for each site, given that this did not result in or any tenant complaints, but resulted in consistent savings. So into the project objectives, I think we've already been through the main one, which is quantifying gas energy savings. Then nextly, the primary objective is to compare different control modes for this project or these sites. And for this application, it was found suitable to use only the 2 control modes highlighted in blue down here. However, should be noted that these are not the only control modes provided by the smart pump technology. There are different control modes dependent on that application, but for this project, we only looked at adaptive learning, which is also known as auto adapt under the Grundfos, but this is more of a generic name used for the report. And then also a constant temperature, which is maintaining a constant temperature along the line itself. So along comparing those different control modes, we wanted to document the costs, they document the implementation, and then also document the tenant feedback upon the different control modes and the different temperature selections that were selected for the setup of these smart pumps. Then also importantly, as mentioned before, we wanted to identify the barriers. Mainly, we found that there was pump oversizing, there was barriers due to upfront costs, and then also that manufacturer guidance, the gaps of guidance provided before, in that you can use this as a plug and play application and then not result in any tenant um, um, hot water complaints. So this technology, essentially, what is the smart pump technology? It's essentially just a constant speed pump fitted with an electronically communicated motor, which allows for variable speed capabilities. And it also has integrated control algorithms so that it can provide smart, quote unquote, smart controls, which are essentially aimed at reducing energy usage and or improving functionality of the system. So these smart pumps obviously offer clear advantages over their incumbents, with being the constant speed uh, existing pumps that these are replacing. Obviously, there is the electricity reduction of 60 to 80%, but more importantly, relevant to this study, and these savings were taken before the study was conducted, it was claimed that these smart pumps can provide up to 7 to 28% gas energy savings. And this is from reduced losses in the recirculation line and reduced losses in the tank, and also uh, uh, the reduced effort of the boilers themselves to actually have to maintain the water, so for recirculation. But beyond that, there's also several different advantages beyond the reduction of energy. Obviously, these smart pumps provide advanced diagnostics capabilities to provide preventive maintenance, um, I guess, methods, just using the flow meter data, the flow data, and also the temperature data to be able to diagnose the domestic hot water system in itself and or the pump. So you could use that as a preventive maintenance measure to monitor your domestic hot water systems for fluctuations in temperatures, flows, or anything that looks unusual. Also, these pumps also have the added capability of having IoT capabilities, which is essentially Internet of Things, which is the communication protocol for smart devices to be able to communicate with each other. So this would be able to incorporate into a larger, say, building management system or protocol, so that you have, say, multiple pumps, and then that you can be able to integrate them into a larger architecture. So again, this is from the study. We only tested two different control modes, which is adaptive learning at constant temperature. To be more to go more into detail, adaptive learning is really just a dynamic adjustment of flow based on its learned demand load patterns. So what it's trying to do is it's trying to minimize the energy by reducing the speed of the pump and reducing the return temperature coming back to the system, and so that you're reducing the actual heat losses in the systems, specifically at low demand times. So the functionality of this pump is that it's supposed to be able to learn when the high demand times are throughout the day, and that it can adapt accordingly to provide sufficient hot water throughout the recirculation line. And so there's not significant wait times for hot water, and there's resulting in tenant complaints. And then also the next one we did was constant temperature, which is essentially a set point control method, which aims to keep a constant temperature within the recirculation line. This is actually modulating between a minimum and maximum temperature. So it's maintaining a constant temperature within a range, but it's overall maintaining an overall average temperature in the recirculation line. And so this again was the preferred control mode, as it's specifically designed to maintain customer comfort, but it also did result in overall energy savings compared to the existing constant speed mode pumps. So it also is to note that the reason why SWW015, the demand response measure package for essential multifamily hot water heating systems, is that the methodology aligns closely with the methodology in this measure package, in that it assumes that the pumps are operating on a constant temperature methodology, in that they're constant speed, but they are turning on and off at certain temperatures to maintain a constant temperature in the line using Aquastat. So it is aligned with this measure package. But it also is to note there are different control modes, such as constant pressure, constant speed, which may or may not be more applicable for whatever site specific application there may be, being that there may be large pressure losses and that you need to compensate for that, and that the adaptive learning and constant temperature are usually not enough, and that you have to resort to a different control mode. But those were not tested in this study. So going into to make sure we're all on the same page, just want to go into a little bit background of what this application is used for and what these smart pumps are. I kind of already explained in general the definition of a smart pump, but what are these? How do these fit into these applications? So again, these are essentially just regular pumps with more advanced capabilities. They have variable speed ECM, basically a motor that can vary in speed instead of doing constant speed application, such as the existing incumbent technologies. And they also provide advanced control algorithms. So the constant temperature versus adaptive learning. To be more specific, the adaptive learning actually uses kind of a machine learning algorithm, kind of proprietary technology. So that's not really something that we were able to get more detail on, but it's essentially was able to use their proprietary technology or algorithms to adapt based on learning the behavior or the draw patterns of the tenants of that site. So it adjusts the speeds, it adjusts flow rates in response to demand or the set temperatures. And essentially, this diagram right here represents a very simplified uh, representation of where the smart pump is actually integrated into these systems. So this kind of represents a domestic hot water system in itself. Here, the HWH is a hot water heater. So that's your storage water heater delivering water through this red line and going up to the tap fixtures. So these are where the tenants would be drawing the hot water. And essentially, these recirculation lines continue these hot water lines and recirculate it back to the hot water heater. And that's where the smart pump comes into play. So the existing technology has a constant speed pump that essentially works to keep this at a temperature that's within 5 degrees of the supply temperature. So it's usually coming back at about 110 to 115 degrees. So it's maintaining a high temperature. However, and the reason why they're doing this is they want to maintain tenant comfort. The tenants need to be able to get hot water at a reasonable amount of time, and these distribution systems can be quite complicated. This is obviously a very simplified version, and so to be able to maintain hot water through this whole line, and so that it doesn't take an extended amount of time for, say, the tenant at the end of this line to get hot water, you want to be able to circulate water through there. However, when using those existing constant speed pumps, you can see when people are not using hot water that results in excess recirculation of water, and it results in excess heat loss from these pipes. And then it also has excess heat loss from the tank. And then also the water heater has to work harder to keep the water from that's circulating through. So what these smart pumps do is they reduce the speed of the pump during low demand times, which essentially reduces these losses in the system and overall saves energy, the input energy of the system. Here, these are gas systems, so our focus is to quantify the gas energy savings. So we can now go into, now that we know what the technology is and what we're using it for, we can go into what the different sites that were selected for this study. So again, this site focused on multifamily buildings with central gas storage domestic hot water systems. We got 12 weeks of baseline data and 12 weeks of post data, so there was sufficient data collected. Specifically, we looked for sites that had a requirement with the return water temperature drop less than 5 degrees minus the supply water temperature. So what this does is that it tells us that a system with a tight differential less than 5 degrees is a well-balanced system, is not experiencing, say, excess heat loss in those return lines. So for us to be able to isolate the impact of that smart pump measure, replacing the existing constant speed pump, we would want a system with a well-balanced and minimal heat loss to be able to isolate the impact of that smart pump retrofit and quantify the true energy savings. So one of the key requirements is that we wanted to see that there was only a 5 degree difference in that return temperature, bringing back that water through the return line, and so we can accurately quantify the savings. Also, the focus of this was on buildings that were somewhat less than 20 to 25 units. So these are all you could see here. Each of these three sites were in CZ03, San Francisco, Berkeley, and also all in the same climate zone. So it allowed for easy comparison across the sites. But we focused on smaller sites. The reason for this is that as demonstrated in the simplified diagram, these sites with smaller number of units tend to have simpler single loops recirculation systems, uh, typically. So, which makes it much easier to quantify the energy savings, as opposed to larger buildings which have multiple loops, multiple pumps, multiple risers, much more complex piping. It could be that they have excess, much more factors of heat loss that need to be considered. So that definitely increases the difficulty to isolate the impact of just a single smart pump retrofit, and then also doing the different control strategies. So the idea was to find smaller multifamily sites so that we can quantify the energy savings more accurately. Again, here you could see the the year built for these varies. The sites 1 and 3 were relatively older sites, while site number 2 was a relatively newer site. Then also listed here, we could see the heating capacity and the storage gallons for these different heating systems in itself. So one thing to note is the difference between, say, site 1s and 3. Site 1 having almost 263 kBTU of heating capacity with 119 gallons of total thermal storage, versus Site 3 that has a fraction of that, even though it's only serving about 10 units. The sizing of the systems is something to note and should be taken into consideration when replacing these smart pumps in these applications. So just to get you guys a little bit of eyes on what we did and give you a little bit of visualization, I'm going to go through some of the site installation photos. So this is going to be for site number 1. Again, this one used, as a reminder, this one used that larger Magna 3 Grundfos alpha pump. So that's what you can see here. This obviously wasn't a plug and play application. It required a custom, I guess, so to speak, Unistrut support installation. So this is obviously not ideal, but due to the availability of just having this pump at the time, we went ahead and used this to be able to start the study. So as you can see here, this is kind of an older basement system, indirect water heater. This is the storage water heater, the indirect gas-fired water heater itself, and then you got the Grundfos alpha pump over in the back behind the water heater. Going on to the site number 2, this is kind of an easier, simpler installation. This is using the Grundfos Alpha HWR pump, so it's a lot smaller of a pump. It's situated on top of these 2 gas storage water heaters, in which this is actually on top of their rooftop structure. So this is on top of the building. You can see here that the retrofit did require a little bit of additional plumbing. However, the amount of installation for this was a lot less than site number 1. And then for site number 3, to give you an idea of the system that we used, over here is the Grundfos alpha pump that was installed. There was not really any additional plumbing that was needed, so this one was really kind of a plug and play application. However, you could see to the photo to the right, based on what we learned from sites 1 and 2, we wanted to actually put in additional water flow meters to be able to quantify the overall system efficiency changes to be able to more accurately quantify the gas energy savings. So I advise, if you want to get more details on this, to refer to the report. Uh, Sites 1 and 2, there were a limited amount of measurement points used based on the initial scope, mainly being gas flow and temperatures. And then by site number 3, it was found that the additional flow meters, which are actually reused from another project, were necessary to be able to accurately quantify the overall effect of the smart pump being installed into the system. So we did find, which was not known initially at the start of this project, that most importantly, you need to know is the amount of cold water going into the system, because the recirculation pump is going to be recirculating a certain amount of water. The biggest effect on the savings is how much reduced energy does it use per amount of gallons of cold city water that's going into the system. So it's very important to note, if anybody's going to be doing these in the future, that getting the water flows is a very critical parameter for this. So to the energy savings themselves, to the meat of the report, you can see here I have split into two: the gas savings on the left-hand side, and then I have the electricity savings in yellow on the right side. So on the left, you could see the gas savings is each site, or each graph is broken down by each site 1, 2, and 3, and then by each control mode, adaptive learning, and then constant temperature. So for site number 1, as you can see, constant temperature, again, did pretty consistent across each site, regardless of size. Adaptive learning showed relatively high savings for relatively high savings for the sites in which it was properly sized. But you can see here the oversized pump, the Magna 3 pump used at site number 1, unfortunately was not able to auto adapt at the low limit flow range that it was seeing. So the system required that it the flow range of the pump, so it wasn't actually able to adapt. So it kind of just floated on low speed, and didn't really provide much savings beyond the existing constant speed pump. But for the other two sites, you can see the auto adapt did provide a relatively large percentage savings, close to 20%. In terms of electricity, the electricity was pretty consistent across each site, again, for numbers, except for site number 1, which was due to that oversizing Magna 3 pump. So now to the discussion. So when we break it down, a clear picture kind of emerges that the adaptive learning has the potential to provide the largest percentage savings, specifically at site 2 and 3. However, it did result in customer complaints for those sites. So there was a balance between finding the lowest return temperature that the system could provide, but still provide adequate hot water to all the tenants so that there was no complaints. So despite the high savings, there was the risk of running into longer extended periods of wait times for the hot water. So that's something that definitely needs to be considered. Something that was also identified here is that the adaptive learning might be suitable for well-balanced, well-designed systems, but not for systems that are, say, undersized. So what I mean by that is, as mentioned in the previous slide, that site number 3 had a relatively small domestic hot water system in itself. So it was not concluded by the data which was collected by this site, but was inferred that the smaller system was not able to provide the thermal storage capacity for the system to adapt down to those lower speeds. So also, it could be that the adaptive learning really isn't suitable for sites that have really infrequent draws in hot water. So the adaptive learning really does an initial learning period, but say if there's a tenant that infrequently draws hot water at times that are not within the learning period, then obviously they'll still experience longer than usual wait times for hot water. So that is something that should be considered when selecting the appropriate control mode. In terms of constant temperature mode, you could see that it provided a much more reliable constant savings across each site, about 8% for sites 1 and 2, and 14 for sites 3. It provided consistent hot water service. Um, and the formatting was a little wonky here. I don't know what happened, but this is supposed to be 10 degrees. But again, as a reminder, that we found that the optimal temperature range for specifically constant temperature, which also works for adaptive learning as well, is that you put it in a range 10 degrees below the supply temperature, whatever that may be, and then allow the pump to dynamically adjust 10 degrees below that, or wherever a minimum temperature could be reached, and such that, say, the last tenant on the line of that recirculation line has adequate hot water in that recirculation line, so that there's not extended period amount of time for the pump to turn on and provide hot water throughout that recirculation line. So there's definitely a balance between, returning a minimal return temperature, which is going to result in significant energy savings, but then also, again, there's the risk of the tenant complaining, and then that kind of negates the fact of the pump, and then the building owners were not so happy with the functionalities of the smart pump. So a lot of times they would prefer that I would switch it back over to constant speed. So that with that in mind, that was kind of the preferred temperature mode. So the key barriers, as stated multiple times, again, was what we found from, without intentionally using the Magna 3 pump. We were not intending to use that, but it resulted in oversizing for specifically site number 1, which demanded low flows that were below the flow range of the pump itself. So unfortunately, was not able to show us any auto adapt performance at that site. So going forward, it would be preferred to using, obviously, the newer Alpha HWR pump, which is more adequate and sized for these applications. Then another key barrier, again, was the manufacturer guidance gap. So it took us a little bit of time to figure out, and it wasn't clear based on the documentation provided by the manufacturer and the installation manuals. It wasn't clear on which temperature limits to use. It was clear that the different modes that which could be used for the different applications. However, it was very important for us to know at the start what would be the optimal temperature limits, so that there's no complaints in the hot water for the tenants, and so that the technology goes adopted without any barrier, really. And then so that comes to the last one, which is the learning period impact. So a lot of times the tenants don't really care how the hot water is being produced. They just want hot water at a reasonable amount of time, something that they're used to. So we found that when there was a change in behavior, that being more time or less, or more time in hot water, and or hot water that's not as hot before, there was resulting hot water complaints at those sites. So it would be good, and it should be noted going forward that selecting the proper temperature limits could be a way to negate that. So additionally, we'll present the costs that are associated with these different sites. So you can see here, broken down into column. There's the overall equipment costs, labor cost, total cost, building size, so that you can give you the cost per unit. It's broken down by each site. And again, you can see that the site number 1 is much larger in terms of magnitude and price cost because of the larger Magna 3 pump that was needed at the time. However, you could see that the relative cost per unit is really not that much more when you take into account the number of units that are served. However, you could see that the relative drop in price between the Magna 3 used at Site 1 versus the HWR at Site 2 is pretty noticeable, in that it goes from about 5,300 to about 2,600. The reason that the site 2 and 3 are exactly the same is that it was the same pump, and also it was under agreement from the same contractor. So um, the real in retrospect, I think the contractor would have priced these a little bit differently, being that one was a little bit less than more than other, but these are good representation numbers to show what the relative cost was for that. Um, but something also not shown here and also not shown in or presented in the report would be the ROI. The reason of that is based on the 16 weeks of data that we had. There were lots of drops and there was a lot of data cleaning that need to be done, and also based on the relative billing impacts during that time. So it was determined that the estimate for ROI would be not as accurate as it should be if we were collecting, say, more closer to a year's worth of data to get a full impact of what the yearly savings would be. But just to be able to provide you guys some numbers, the ROIs are ranging from about 3 to 5 to almost 10 years. So they're within reason, but however, that's not something that was presented or as a focus of the study. So really, it's just to quantify the actual energy savings per unit and to be able to support the statewide energy measure pack, the statewide measure packages to be updated. So in terms of future recommendations, we have kind of several recommendations based on what we found. Um, we would like to essentially adopt into energy efficiency programs. So adopt the smart pump using updated measure packages. So updating relevant measure packages using the different findings and recommendations used from this. So it should be noted in these measure packages that the preferred uh, control mode that would be used for the for this study, the default would be constant temperature, as this didn't result in any tenant complaints. However, it wasn't fully concluded that auto adapt wouldn't also be a preferred mode of uh, the smart pump. It's just based on what we found. We found that constant temperature was the preferred mode. So another core recommendation would be to engage with manufacturers specifically to provide more clear literature and temperature setting guidance on different site-specific applications, specifically domestic hot water applications, so that there's obviously the tenant comfort is maintained, and that the installation is a lot easier so that they're not constantly having to optimize the controls over so much amount of time. That would obviously be a barrier. So then another core recommendation would be to continue to do future studies and contractor training. So again, this study only uh, was only conducted in climate zone 3 due to uh, the the limited amount of customer uh, involvement. So it was very hard for us to get sites to be recruited on here, specifically because a lot of the sites were not willing to modify their systems for the little benefit that was promised from the upgrading to the smart pumps. So it was found that the 3 sites that were willing to actually um, study were all within the same area. Um, so that was fortunate, but the future studies should consider obviously different climate zones and then also different site specific applications. So being different types of domestic hot water systems, uh, specifically gas water heating systems. So then the last one is that there has to be a balance between hot water service and gas savings. So that's a huge priority here. Is that the core recommendation is that you want to reduce the hot water coming back to the system to increase the energy savings. However, you want to maintain that hot water service so that the customers are not complaining, and that at the end of the day, if what we found is when a customer start complaining, the on-site maintenance would simply turn up the set points on the hot water heaters, and then that obviously would negate the savings and would uh, negate all the whole reason for the study. So it was really important to prevent those hot water complaints, so that there was no preferences to increase the temperatures and obviously modifying the system so that quantifying the savings would have been very difficult. Um, Lastly, there's the M&V recommendations. So we did find, based on what from our 3 different sites, that it was required to have advanced instrumentation at a retrofit isolation level, so specifically the water flow meters. So it's recommended that if anybody were to be doing this study in the future, not to only capture certain parameters, but to capture all the system parameters to identify to accurately quantify the gas savings from, say, reduced recirculation losses or reduced tank losses or any other components in the system for that site-specific application that the spark pump is actually impacting. So depending on the system itself, it's recommended that you go ahead and use the advanced instrumentation if not already there, and then also to follow NREL MMV practices to quantify savings. So the way we did quantifying savings throughout each site is we were able to normalize the gas energy usage per the actual demand load. So for the first 2 sites, this was done by normalizing based on the parameters that which we had, being temperatures. So it wasn't as accurate as it was for the site 3. However, we were able to use the additional parameters in site 3 to be able to accurately normalize the gas energy savings for, say, per unit volume of water being introduced in the system and or cold water, cold makeup water being reintroduced in the system. And so we were able to use those findings from site 3 to be able to validate the savings that were found from sites 1 and 2. So it does that meaning the savings from site 3 were similar to the savings at sites 1 and 2 using the different methodologies. So that is something to note, and that is outlined in the report itself. So if you do want more information on that, I do recommend that you go and read through the report, as there are it's pretty detailed on that aspect, on the different ways that we went about. But essentially, we're trying to follow the NREL standard practices for quantifying energy savings by normalizing the gas energy usage per the demand of the system, so that when we replaced the smart pump, if they were using a lot less water or energy, then the smart pump wasn't just simply showing that it wasn't it was normalizing for the load and such that it would show what would be the existing pump using at that same low load. So this is I didn't go into detail about that into this report or this presentation for the sake of time, but again, I would really recommend that if you want to know more about that. You can go into the published report itself, which provides all the values and methodology and equations and everything that's used. So it provides as much transparency as possible if you would like to know more about that. So I think that is the last slide of the report, or the presentation. So I just wanted to give, if you want more information about this project and obviously the published report, I'd recommend going to ca-gastech.com, or also you can use this email here and email any questions that you have. So this is obviously led by SoCalGas, but also this is the statewide effort that is also supported by the other utilities as well. So San Diego Gas Electric and Pacific Gas and Electric Company, that are also gas utility companies. So thank you. If we can go back and leave time for the Q&A.
Thanks, Chris. Just checking if you saw John's question in the chat or Q&A about gas savings. How were gas savings calculated year-over-year gas bills?
Yeah, so John, we didn't actually do any year-to-year annual gas savings. So we did a projection of baseline into the post period to show and normalize for the actual gas usage in itself, and then we compared what the existing pump energy usage would be versus the actual measured smart pump energy usage. So what we did, we were able to monitor the baseline energy usage and normalize it for the baseline pump, and then projected that into the post period using the smart measured gas data, and then use just a simple percentage difference between the days that were collected. So we didn't really do any projections into what would be obviously the yearly expected results. In the report, there is an estimated based on the average daily energy savings, but really it doesn't go into detailed annualized calculations, if that makes sense. But I would refer, if you'd like to go back to the report, it gives you a clear outline of how everything's calculated. And then we also have Scott Campbell from Act Controllers. Hi, Scott. And then he says, so what was the specific guidance did Grundfos give regarding the auto-adapted function, IB incomplete as noted in this presentation? So we did get a little bit of mixed feedback from Grundfos. They did recommend, so initially they did recommend that AutoAdapt could be used for these applications, but then we also have received feedback that it's preferred to use the constant temperature mode. So it seems as though they don't want to say that it doesn't work, but that they still prefer constant temperature mode be used in domestic hot water applications. This is like briefly mentioned in the materials, but it seems it would have been better if it would have been more clear that AutoAdapt can still be used, but there's risks and limitations into implementing it. Kind of similar to demand controllers in themselves. So it would have been better to have clear guidance on the different temperature limits such as that, so that we could just essentially prevent any tenants from complaining from insufficient water. Another thing to note, Scott, I know this has to do with the controllers, is that we didn't test for any crossover in any systems. So these systems were assumed to be operating, the way that we expected, but we didn't test for any crossover or anything like that. So that's not something that was, considered in these applications. And so I think the next question, have you looked at the GTI reports on demand systems? So I have not, Scott. So that'd be interesting. I would like to look at that. So we have been in touch with the Grundfos secondarily, and so they should be providing me with some more information on what their guidance is. However, obviously it's a larger company, so it's a little difficult to meet with some people, but we're still kind of following up on that to make sure that the information that we're giving on these presentations is it's true to what they want to give. But unfortunately, we haven't had any clear guidance from them. We did speak with the I think it was the president, and he did give us those recommendations on the constant temperature modes. However, we have received different feedback from different areas of the company, so it's a little I can't be clear and cut on what the feedback we got from them, but from what I got is that AutoAdapt can still be used, and they still recommend it can be used. However, for certain applications, specifically domestic hot water, constant temperature mode is preferred to start out with, and then adapting to AutoAdapt later would be something that you could do. But yeah, I hope that answers your question.
Great. Looks like. All right. No other questions for now. Well, if there's no other questions, thank you so much, Chris, for doing this presentation. And if anyone has any questions, please feel free to email our contacts which I can drop in the chat. But otherwise, everyone, thank you for joining.
Thank you, Chris. Thank you, Kate.
Thank you, everybody.